top of the hour here in Madison, Wisconsin, and we're going to give folks just a few more minutes to join in. We've got a really large group that's registered for this town hall. So give us just another minute or two, and then we'll kick things off. In the meantime, we've got a message about following us on LinkedIn. If you don't already follow our department, your alma mater department, on LinkedIn, and if you're on LinkedIn, we'd love to have you follow our updates there. And also there's a QR code here if you want to take your phone camera, if you've got one handy. We'd love to hear from you. We've got a form that you can fill out to let us know how you, as one of our beloved alumni, how you'd like to engage with ECE going forward. So grab that QR code while we're giving folks just a minute more to join us. Would also love for someone to take the plunge and dive in there on the chat and let us know which city or town you're joining us from and what year you received your ECE degree from UW-Madison in. Thanks, Nate, for being the first one to chime in there. Welcome. Where's everyone else from?
Concord, Massachusetts.
Oh, great. And Joel Johnson, I have been to your town. I'm guessing you might know Alejandro Puig. Joel Johnson, do you know him?
It doesn't ring a bell.
Doesn't ring a bell.
No,
Okay.
no.
Again, welcome everyone. We're gonna kick things off in about 60 seconds. In the meantime, take a moment to grab that QR code if you'd like to let us know how you'd like to engage with us as one of our alumni. And also let us know where you're joining us from. You can do that in the chat. All right, well, I'm going to go ahead and kick things off because it's 12:03 Central Time here, and we've got a lot of really great information to share. It is my great pleasure to welcome all of our ECE alumni to this winter virtual town hall. And today's town hall is focusing on a very timely theme of energy systems in a world in which our usage of AI is really escalating. And this theme is the intersection of two core research areas within ECE, both energy systems and AI. And these are areas that are also high demand in instruction. And so our class enrollments in energy systems and in AI are really at an all-time high. So it's my great pleasure to introduce you to 4 members of our ECE community. We have Associate Professor Lena Roald, who is an expert in power systems engineering. And she is in high demand as a speaker because of her technical leadership in the field of energy sustainability. In fact, she recently spoke at the National Academies of Sciences, Engineering, and Medicine at a workshop on the implications of AI-related data centers, electricity use and emissions. And we are also joined by 3 of our current PhD students in ECE, Asmita Paul, Elise Song, and Jaewen Pan. This trio won first place in a recent competition that was sponsored by the UW-Madison N+1 Institute and also Google. It was a reverse pitch competition, and they won first place for their pitch on an AI sustainability solution. So we're going to be hearing more about their work as well. So without further ado, I want to turn things over to Lena Roald, and I'm going to stop sharing my screen and let her share, and she'll fill you in on her thoughts on this really timely topic of energy sustainability in a world in which we have ever increasing demands for AI computation. Lena.
Thank you very much, Susan. It's great to be here and very nice to see that so many have joined us here today to hear about this topic. So yeah, also welcome from me. As Susan said, I'm an associate professor in the department. I've been in Madison for about 6.5 years now, and throughout that time, data centers and their interactions with the electric grid has been a focus of my work. And it's been very interesting to live through the last couple of years and see this rapid acceleration, which I don't think is surprising, but you know, when it hits, it hit hard. So, okay, so I will take a few moments here in the beginning to talk sort of a little bit generally about data centers and their increasing energy use. There's so much happening so quickly that there's a lot of things that we are working on in this space. And I want to kind of give a little bit of context there just to recap that and make sure we're all on the same page. And then I will talk a little bit about some research results that we have from our group related to data center energy use and sustainability, and in particular carbon emissions. So first, I wanted to put this map up here to just show where data centers are in the United States. So this is from Data Center Maps. And you can see that there are very significant sort of groups of data centers along the East Coast. In particular, Virginia has a very high concentration of data centers. There's also a large cluster in the Midwest, particularly Ohio, and also you can see around the Chicago area. That is, you know, lots of data centers, and you can see also throughout the country, as it is now, there's a kind of a growing number of data centers. So we know that data center energy use is growing rapidly. Some of you might have seen these headlines. We kind of know that when the Washington Post and New York Times start talking about talking about the grid, generally, the grid is not something people think about until it becomes a constraint and a problem. And so essentially, these are some headlines from last year around this time, just pointing out how the rapid increase in electricity demand from particularly data centers and also their clean tech manufacturing, in particular battery factories, is really straining the electric grid and also kind of causing questions around how we are going to actually be able to power this new infrastructure. So although this has sort of already been a large growth in data centers, it's showing absolutely no signs of slowing down. So I wanted to kind of take a little bit of a historical perspective here and talk about some of the underlying trends that are happening. And so if you look back at data and projections of data center use, in particular, there's a group at the Berkeley Lab who's been doing a lot of work on trying to estimate data center overall energy use. And they found that, you know, in the decade from like 2010 to 2020, or maybe until 2018, there was large increases in computing use, but we didn't really see a lot of increases in energy use from computing. And this had a lot to do with the fact that efficiency very rapidly increased. So in particular, as computing workloads moved sort of from smaller data centers, maybe on-site locations for different companies, more into the cloud, where we get these really large hyperscale data centers, there was a huge increase in efficiency. And so that sort of masked the impact of this increase in computing use. So from around 2018 onwards, I mean, a lot of these larger efficiency gains had already been exploited, and we were starting to see that energy use was sort of more closely tied to how much computing we are using. And that is sort of what we are expecting then kind of moving forward, is that as we use ever more computing, it could translate into ever more higher electricity use. Of course, there is still hope for you know, continued efficiency gains, and who knows what will come about, as we will hear, I think, from our next speakers. But essentially, some of these very large gains have kind of been exhausted. And so we were already seeing that that electricity use was going up more rapidly. And then, of course, in November 2022, ChatGPT was released. And we see this explosion in use of AI, the need of resources to train AI models, the need for data centers to do inference. And so that is kind of where we are right now, right? Is that there's a lot of promise in AI, and depending on how things move out, there's a large range of uncertainty around exactly how much energy is going to be needed by data centers in the near future. So just if you look on these projections until 2028, you can see that we are going from in 2018 having about 2% of total US electricity consumption going to data centers to just a decade later talking about something in the range of 10%. There's a big uncertainty here, 6 to 12, but still very, very significant. And so, I mean, we can also hear, I mean, also just in the last few weeks, we've heard a lot of announcements of new investment in data center infrastructure. So we have things like the Stargate project, which promises to invest 500 billion over the next 4 years, and also other large actors like Microsoft. And these are just a couple of examples of just incredible sort of indicators of this incredible growth and how it is likely to continue. So what does this look like for the electric grid? So that is what I focus on. So first of all, it's kind of helpful, I think, to just take into account how much electricity this is. So in parts of the country where there's a lot of data centers, like Virginia, already around 25% of all electricity is currently used by data centers. And this number is set to continue to increase. There's a significant number of data centers that have already contracted with the utility in Virginia. And there's also significant plans for expanding the grid in Virginia to accommodate this data center growth. And so you can see this headline here about doubling the amount of data center capacity. And you can say if you double from 25% of electricity used from data centers, that becomes a very significant portion of the total electricity consumption. So what has happened is that because, for example, the grid in Virginia is quite congested with all these new data centers, the data center companies are increasingly expanding into new areas around the country and sort of essentially trying to figure out where can we get contracts for electricity, because electricity is really becoming one of the main constraints on building this infrastructure. And so there's also, I think, the electric utility industry has certain ways of developing projects. And it is interesting to see that industry now meet the tech industry, which comes with a lot of resources. And we see a lot of new kind of constellations and tactics that are being used to secure electricity. Like, for example, the headlines from last fall, where Constellation Energy signed a contract with Microsoft to restore a nuclear unit on 3 Mile Island to provide more carbon-free electricity for their data center. So in my world, I mean, when I talked to utilities 2 years ago, most utilities didn't really say very much about data centers. And then in the last 1 year, it seems to be everything they can think about. So it's been like a very significant shift in terms of what this means. And I also was just want to say, we're in Wisconsin. Of course, this is also a big topic here. So we have a new Microsoft data center in Mount Pleasant. And there's also, there will likely be several other large data centers built in that region. And just this one Microsoft data center is using enough electricity to power 300,000 homes. So 450 megawatts of power. And one thing that happens then is that we need new sources of generation in order to to generate this electricity. And so the other headlines that you can see on this slide have to do with the cost and sort of investments that are happening into building new infrastructure. And that there's a lot of questions around how these new infrastructure is going to actually impact cost of electricity for all consumers, because investments are being socialized and, you know, might increase electricity rates. And then also potentially also emissions, because as, for example, V Energies is looking towards building new natural gas power plants, we are unfortunately also kind of locking ourselves into an electric grid with more fossil fuel generation that will likely be generating power for a long time to come. So kind of significant questions here around like who will bear the cost, and also to some extent, how much of this new capacity in data centers is actually going to be realized. I mean, there could also be situations where if the AI boom doesn't continue the way it's expected to, how maybe we could end up with sort of an overbuilt grid that is more expensive than necessary. So a lot of questions that are needed to figure out, and which we think a lot about in our research, but also a lot of things that are just happening very rapidly in real time here. So I talk here on this slide about how utilities that host a lot of this new data center capacity tend to turn to natural gas generation in order to support increased generation. But what we also hear is that tech companies want to be green. So we have very public announcements, for example, from Google, stating that they want to be operating 24/7 carbon-free by 2030. And there's also a lot of other focus and other similar type of announcements from other companies. So there's, questions about how you can achieve this. But one of the questions that we have been exploring in our research is whether or not it's possible for data centers to use some of their flexibility to try to reduce carbon emissions and essentially rely more on low carbon energy. And so to understand the opportunity that is there, I want to take a step back and just talk about what is actually the carbon footprint of electricity consumption. So we know well that electricity generation produces carbon emissions. So if we have large generation like natural gas, that produces emissions, and those are kind of then inherently bound to the electricity. Then we also know that with increasing renewable energy, those emissions are going to be time and location varying. So for example, in the times when we have a lot of sun and wind, we are going to see that we might have lower emissions and more available renewable energy to use. And so this essentially creates an opportunity for consumers to try to adapt their electricity use to the times and locations where there is low carbon energy available. And we are seeing a lot of interest in this. And so the question that we've been trying to answer is, what should I do if I'm a consumer? I can be just a person like myself, or I could be a large data center operator. And what should I do if I want to contribute to a greener real-time grid? And so the answer that many consumers come to is that it would be great if I can just know what is the carbon content of the electricity that is being served to me through my plug. And so we are seeing a lot of like consumer-facing devices. I mean, for example, iPhones having clean energy charging by default. We are seeing Samsung SmartThings, for example, helping adjust in-home electric loads to times when there is lower carbon energy available. We see larger things like Google shifting data center load. And I put a little bit of a picture here on this slide of a little light bulb that shows green when the electricity is green. And so essentially here, the aim for consumers would be to use electricity when it is low carbon. The big question here is, does this work? And I want to talk about like, why is that even a question? Because it seems very logical. And the answer to that question, short answer, is that it's unclear if this actually works at all. And the underlying challenge is that although we know that generators produce emissions, it is not directly clear which consumer is getting their electricity from which generator. And so essentially the allocation of carbon emissions from this generator versus this, from the natural gas generator versus the wind power generator, how that kind of flows through the grid is very hard to define. So there are standards for how to do carbon accounting for electricity, and this is typically based on average emissions. So this is based on the greenhouse gas protocol that is very widely used. And average emissions is just total carbon emissions in an area, in a region, divided by the total electricity use. And you can see here an example of data that showed this average carbon from electricity map. So this was pulled earlier this year. So if I now know that I can assess my emissions using this average carbon emissions, my first step is to count my emissions. But the next step, as we discussed, would be to take an action to reduce emissions. And the thing that we wanted to answer is if, for example, a data center takes an action to reduce emissions, what happens in the grid? So to analyze the impact of data center load shifting, we were using a model of a power grid with 1 year of data. So you can see a schematic picture here of a geographical region with a power grid. We have some in circles in red that represent data center locations. We have several data centers in this area, in this grid. And essentially, we are allowing these data centers to adapt where and when they process their workloads. And by shifting where and when computing is being done, this could, for example, be delaying training of a machine learning model or shifting the location of inference workloads. We can also adapt the electricity use. And so by allowing these data centers to shift and essentially in response to these carbon signals, we can let them try to reduce their emissions. And so what happens when we do this? We've run results for this across the whole year. And what we observe is that if I let a data center kind of do this load shifting and try to adapt its energy use to minimize its own emissions based on average carbon emissions, the total carbon emissions that are allocated to the data centers are reduced by a substantial amount, by like almost 4%. However, at the same time, what we observed is that the total emissions in the grid actually went up. So although the data center thinks it does something good by shifting to a lower carbon area, if you do that according to this signal, the total grid emissions can increase. And so this kind of tells us that using average emissions as a way of accounting carbon emissions is maybe not a great idea, because the incentives that this specific metric gives us can lead consumers like data centers to believe that they contribute to lower emissions and also are assigned fewer, while their actions actually increase emissions in the grid. And so that I find that very concerning. And so this is kind of a topic that we are working on, both because it relates to data center, but also more generally to electric loads and how we understand the carbon emissions of our electricity use. So there are other metrics that hopefully can be better than average emissions, as this is ongoing research in our group. A couple of other directions that are maybe also more directly tied to the AI boom is that these are directions that we are currently exploring, are questions such as whether or not AI data centers can help the grid. And here I mean by really like physically do this type of shifting. So for example, there is scope for data centers to help ensure balance between consumption and production of electricity across different timescales. They could adapt their power use based on a general availability of power in the grid, and also help, for example, manage short-term power use to provide regulation and reserve capacity. And so here, this is a picture over here by Google, which is showing how Google data centers could be able to shape its load profile in response to grid signals, like, for example, price and so on, and thereby help the grid operate better. And another question that is also important is in what ways maybe data centers could damage the grid and how we could potentially avoid such damage. And examples of ways in which data centers can be harmful to the grid would be through very large power swings. And so you see here an example of some power swings. This is on an 8-node training workload. So this is a small one, but you can imagine there are, because when you have these swings in power use that you can see on the lower picture, you can imagine that these amount to quite large changes in the grid if they sum up across very many nodes in a data center. And so because these type of swings become synchronized when we are looking at training of large language models, then it can have a very substantial impact on the grid. So these rapid changes in power use, questions such as how they impact grid dynamics and stability are also things we are very interested in and currently looking to explore. So yeah, with that, I'll end my presentation, and thank you for listening.
Lena, thanks so much. So we already have some questions coming in, but I'm going to turn things over now to our trio of 3 ECE PhD students who just recently won first place in a reverse pitch competition that was sponsored by Google, run through our UW-Madison N+1 Institute, focused on AI sustainability. So again, let me introduce you to Asmita Paul, Elise Song, and Jaewon Pan, and I'm going to have them take things from here.
Hello, everyone. We're Joanne, Elise, and Ashmita, PhD students in the ECE department with a focus in computer architecture. So last November, we participated in the N+1 Institute reverse pitch competition here at UW-Madison. The computer science department partnered with Google to challenge students to propose solutions for reducing the environmental impact of data centers. So as demand for data storage and processing continue to skyrocket, the carbon footprint of data centers is a significant challenge to achieving global sustainability goals, which is something that Google cares about. The topic happened to align well with our research, so we submitted a proposal and were selected to give a reverse pitch. It's an 8-minute pitch in front of a panel of professionals like Shark Tank. It was such a fun format, and it's so cool to see other students and departments at UW-Madison tackle the problem from data center infrastructure to an app raising awareness about emissions. So with that, let's dive into our proposal. Instead of focusing on power or energy efficiency, we look at sustainability at a very different angle through our idea of bringing good enough computing to the cloud. But before we jump into the details, let's start with a quick visual test. Here are two images of a parrot. Next slide. Oh, sorry. Can you spot any difference? In fact, the right image has lower precision than the right, but the difference is barely noticeable. So the full precision image on the left might actually be an overkill for many applications. Similarly, in computing, perfect quality isn't always necessary. So this brings us to our topic today, how good enough computing can help reduce environmental impact of data centers. Embodied emissions due to manufacturing contributes to a vast majority of data center carbon footprint, if assuming running on 100% renewable energy. Among these, memory devices like DRAM and SSDs contribute significantly. Therefore, we propose to amortize the embodied emissions of these memory devices by extending their lifetime. But before that, let's quickly cover some background on reliability engineering. In a data center, reliability starts at 100% and degrees over time. To limit failures, data centers are yearly decommissioned after a set period, within which reliability drops should be minimal to keep the maintenance cost low. Now, if we always want perfect quality, we have to close the gap between the actual and perfect reliability levels. So this means repairs and replacements to bring the system's virtual reliability back to 100%. To achieve our goal of reducing embodied emissions, we can extend the data center's lifetime. However, if we do it naively, maintenance costs will increase dramatically. So what can we do without constant repairs? Recall from our parrot example, perfect quality isn't always necessary, so we propose taking advantage of the air tolerance nature of many applications running in the data center, which allows us to maintain a good enough application quality. Let's dive into how this would actually work.
So we propose to reduce data center environmental impact in 2 stages of its life cycle. First, we reuse memory hardware to amortize embodied emissions, and second, increase memory lifetime through a software solution. The reused and aging memory devices may be unreliable, so any failures are tolerated through good enough computing. In our scheme, a data server is made up of power-efficient CPUs or GPUs running on renewable energy. To amortize embodied emissions, we pull reused memory devices from decommissioned servers and join together for larger bandwidth to enable memory sharing across multiple servers. To run an AI application, we split the program into smaller stateless functions, which cooperates well with good enough computing. A stateless function can be rerun if the output quality is deemed not good enough without impacting other functions. Say the first function inverts the color of a vector in an image, turning the red parrot into a scary blue parrot. So pixel data can tolerate errors in memory, so we say that the input and output vectors are amenable to approximation. However, something like a counter in a for loop should not be approximated, since it would affect program structure and flow. All of this information is compiled into an error tolerance heat map for every value stored in memory. So the vectors are characterized as error tolerant in dark blue, and the for loop counter is characterized as error intolerant in light blue. Given our pool of memory devices with varying levels of aging and degradation, we use a DRAM aging model to quantify the reliability of each device and create a memory reliability heat map shown in orange. We take the two heat maps and map error tolerant data to unreliable hardware and error intolerant data to reliable hardware. If the output quality is not good enough, we can restart the function with a new and more reliable memory device mapping until it is good enough and we get our blue parrot. So now we can switch over to a breakdown of cost to integrate good enough computing.
So this graph shows the accumulative cost in terms of millions of dollars for operating a data center from 2022 to 2030. And we can see that there's an increasing trend that can be attributed to the excessive compute demand for AI applications. On top of this plot, we have manufacturing costs based on how frequently server equipment is replaced in data centers. We adopt a lifetime of 4 years based on prior work and published reports. These manufacturing costs are the primary contributor of embodied emissions that we saw in our earlier slides. Google revealed that in 2021, it adjusted the useful life of its servers from 3 to 4 years and some of its networking equipment from 3 to 5 years. And this led to a 2 billion increase in net income and also a 2.6 billion reduction in depreciation expenses. Now, there might be small repairs from time to time to maintain server equipment, and which include CPU sockets, memory modules, and fans. Even optimistically, 22% of servers undergo repairs in their lifetime. This is a small fraction compared to the operational and energy cost. So let's look at some of the costs for our proposed good enough approach. Here we assume that same operational costs as the baseline. On the other hand, manufacturing costs are lower due to an extended lifetime of 8 years. Also, 35% of repairs belong to memory modules, and hence we reduce them proportionally in our approach, assuming we will operate on older hardware. Now, this is the most optimistic scenario where outputs of good enough computing is always acceptable. Often, this is not the case when outputs are not good enough and you incur additional runs to reach a desired outcome. Additionally, running on older hardware means higher energy consumption, and combining such factors, we estimate an upper bound for overhead numbers based on prior work. Here we see that in subsequent years, overheads from a good enough computing approach add up, and eventually server equipment will need to be replaced in an event there are too many failures. So these are some of the topics we actively work on, which directly or indirectly impact sustainability and adds to the concept of good enough computing. And from the competition, as well as from some recent conferences that we have attended, we do believe sustainability is a big factor in designing the future of computing systems. And to conclude, we really enjoyed pitching this on the reverse pitch platform provided to us, and we're happy to take any questions or feedback you have for us now.
Wonderful. Thank you so much, Asmita and Elise and Jaywin. So I want to open up this town hall now for questions to come in from our alumni. For any of our presenters, you can direct questions to Professor Lena Roald, or you can address your questions to this a trio of 3 ECE PhD students who won this reverse pitch competition. We did get one question, just to kick things off. We got one question in here about work done in the possible use of green hydrogen to power AI centers. And some of our alumni have chimed in with some of their thoughts on that. But I'm going to turn to Lena Roald to see if she has any comments on that question.
Yeah, so I can see that there are, also comments in the chat that says that there has been work on this. I am not like generally aware of this as like a major solution. I guess that, I mean, I know from what I know about AI data centers and the type of power backups that are available, I mean, it's more common to, for example, leverage batteries in combination with, for example, renewable energy. And part of that is that the round trip efficiency of battery charge and discharge is higher than the production of hydrogen and then, creating electricity from that again. But yeah, I cannot comment in detail more, and it looks like there are some good links in the chat. So maybe those would be good to explore.
Great. So alumni, would anyone like to ask a question? If you would like to unmute yourself or raise your hand, we'd be happy to entertain a question submitted that way. Or if you prefer to put your question in the chat, that's welcome as well. Any other questions for any of our presenters here?
Yeah, I have a question. I'll blank out. Oh shoot, what was my question?
So Robert, you know what? Come up
Senior
with your
moment.
question. That's okay. Come up with your question. We'll give you a moment to regroup and think about what
Okay.
that question was, and I
Let
can
me-
ask it.
Yeah.
Okay. So while you're coming up with that question, I'm going to turn to the questions that were submitted in advance. I've got one. And that is a question that was submitted by Misty Kurek. Is UW
Oh,
looking at...
I remembered my question.
Okay, Robert, go for it.
If there's 300,000 homes, how many homes do we have in the whole state? That's quite a huge facility and if this is just the beginning or are some of these centers in place supply us for a while, or is this exponential curve going to continue upward, and are we going to be at the point someday where we have more electricity going to AI centers than to houses in the whole state of Wisconsin?
Great question, Robert. Thank you for asking that. And we'll go with Lena. You want to tackle that one?
Yeah, sure. I guess it was, yeah. So specifically the number of 300,000 homes has to do, I mean, it's related to this new Microsoft data center in Mount Pleasant. And this is, I think, it's the number of, like, in terms of power, that data center is expected to consume 450 megawatts of power. So that's a fairly sizable power plant that would essentially then be kind of just serving a data center like that. And I mean, 300,000 homes, that's about the size, I guess, of Milwaukee, or like, I mean, in that order of magnitude at least. So yeah, definitely the data center in Mount Pleasant is going to be the largest electric load in Wisconsin, I think by a quite large margin. And we can imagine that, then assuming that there are other data centers that get built around the same area, that is going to very significantly increase the electricity consumption in the state. And I don't know if we would yet get to the point where it would be more than what is provided to all households, but maybe we would get close. And so I think it is definitely a very significant electricity demand that is needed, that comes from these data centers. And we might not think about that, but for example, this meeting requires a lot of computing, and that is happening somewhere. So although we don't see those emissions and this computing and the emissions and the energy use associated with that, of course, anything we do kind of online also requires compute. And so yeah, so there's a relation, of course, between how we use computing and how much electricity we need for it. And so whether or not the exponential curve is going to continue, that's a really good question. That's a very important one, and one we don't really know the answer to.
Thanks, Lena. So we've got a lot of questions coming in now on the chat. Let me see if I can pose these one by one. So we have a question that I'll pose to the whole team of panelists of sorts here. Maybe the students can jump in as well. Is the maintenance needed to match reliability levels desired hardware related or software related?
So I think maintenance related to hardware related maintenance is probably still required, but the idea is that we hope to reduce that as much as possible by having a lot of like non-perfect hardware, if you will, in the data center, and the point is that they can be still useful. So instead of constantly fixing and replacing your like aged hardware, maybe there's way that they can still be useful for the non-critical data processing, for example. That's our idea. And the software related maintenance, we'd like to view it as a overhead, like software overhead. Maybe this is a piece of software that's running on the data center that's doing the scheduling for critical data. You want to run them on your reliable hardware and the non-critical data on the unreliable hardware. So we see it as like an overhead instead of maintenance.
All right, great. Thanks for addressing that question. We've got a question about what is the average cost of a single kilowatt per hour for an average data center?
Yeah, I don't know if I am really able to answer that based on, I mean, these are, of course, negotiations and contracts that are happening between utilities and the data centers. I think one interesting thing to know about like the contracts that are being signed, and one of the sort of things that are happening, we are seeing, for example, in Ohio, that the utilities are requiring contracts where the data center companies, the companies that build the data centers, they have to commit to paying for the electricity that they are saying they will use, or at least a certain percentage of the energy that they say they are going to use, even if they end up not using it. And so these are contracts that are being put in place in order to make sure that even if, for example, a data center wouldn't get realized and someone decides that actually we will not build that data center here, that the costs that are going into building new infrastructure for that data center would still be recovered, in part at least, by the company who sort of said they were going to build it and thus started the whole process of getting that infrastructure built. So
Great,
that's
thank you.
maybe related, but not exactly.
Yeah, lots of good questions coming in here. Next question is, what impact could having less energy intensive AI applications such as DeepSeek have upon the AI energy resource issue? Are the savings DeepSeek developers promise meaningful in your analysis? Anybody want to try to tackle that one?
Yeah, sure. Yeah, so that's a really good question. So I think, yeah, if you can handle something like on the application level itself, on energy savings, that's great. But essentially what we exploit this very like aspect of AI itself that, you don't necessarily need to be 100% accurate. Like, when you're searching like, oh, tell me this, like ChatGPT or like, let's say DeepSeek, you're making a query, user one might be happy with it, user two may not be happy with it. So it's again like a bit of perspective. So it's a little more user oriented, I would say. The good enough, like, if the result is good enough for you, you go away. Like you have like, some kind of energy savings. What we also thought about in the process is like, like future data centers could have this model that, oh, are you okay with like, your result being 80% accurate, or like train something to like 80% and contribute to sustainability, have like use like 50% less energy, or do you still want it to be 100% and use 50% more energy? So some kind of incentive like that might play into that. And yeah, so definitely if you can tackle a little more at the application level, it would add to our analysis of the good enough computing.
Thank you. Here's a question that goes in a bit of a different direction. Any energy harvesting opportunities through heat dissipation that are gaining traction?
So I'm not aware of specific energy harvesting. I mean, I don't know if I am reading the question correctly, or if it is better in my area or others. But I think that there are data centers, maybe a little bit less in the United States, but like, for example, in Europe, data centers that are getting built in colder locations. Like, for example, the town or the city I grew up in, Oslo, in Norway, which is a equally cold place to Madison, where you build a data center and you can leverage heating from that data center for district heating. So you are able to provide heat to people around the data center through district heat system. So that is one way of course, then making better use of that heat. So it's not directly, I guess, an energy harvesting, but to some extent, maybe, yes.
Heat dissipation redirecting. Yeah, great. We've got a question about, in a typical data center, what percentage of electrical power is used for processing AI power and what percentage is used for cooling purposes? I hear a lot of water is being used to cool processing systems.
Yeah, I could speak a little bit about that. I mean, I might play that Ashmita and Elise and Siobhan would be better at talking about some of this, but certainly there are numbers that indicate essentially how much of energy use that goes into data center are being used directly for computing tasks and how much is being used for other things like cooling. And so this is a number that's captured in a number called PUE. And that number has gone from sort of indicating that like maybe close to half of what of all the energy use would be cooling about maybe 15 years ago to today, where we are looking maybe more at around like 10% in these like more efficient data centers. And so the cooling has become much more targeted. It is much more focused on like where and when computing is happening. And so this is also one of the reasons that if you are going to adapt energy use with data centers today, you really need to think about how you are going to work with the workloads and the computing tasks themselves. It is not only, it's no longer feasible, as was kind of explored maybe 10, 15 years ago, to, for example, do pre-cooling and other kind of like work only with the cooling systems, because they are so closely linked now to increase efficiency. And yeah, water is definitely also an important aspect. I mean, for example, just here in Wisconsin, there are concerns about that, a data center like the one in Mount Pleasant could be using a lot of water on hot summer days, and which might have negative impacts on, for example, the Great Lakes if that is being pulled from there, and also on just like the water systems in the area. I believe that there's new technology that is looking more at sort of closed water cooling systems, and that would maybe reduce the amount of water that would have to come into the system. So instead of like, for example, evaporative cooling, you could like have closed loop systems that allow for less water to be used. And so those are, but water cooling is part of like what has helped achieve those large efficiency gains.
Great, thanks, Lena. Charles, you've got your hand up. Let's go to a question that's coming in real time here.
Thanks, Professor, and thank you so much for the compelling talk. My question has to do with the economic value of the equipment in a data center. I think a 100 megawatt data center may have $3 or $4 billion worth of NVIDIA GPUs in it at their current prices. How do you convince people to sort of strand that resource? You're going to strand a piece of that resource if you're shedding load based on powering down or reducing the clock rate of those GPUs. If it's billions of dollars worth, you know, people can buy a lot of electricity for billions of dollars. Is the green initiative and the green efforts alone enough to do this? Or do we have to, you know, figure out some other calculus to actually motivate the behavior that you're asking for in your graphs?
Yeah, no, that's a really, really good question. And I think like essentially the question of like, how does capital expenses, like building the data center and buying the GPUs, how does that relate to operational expenses, which are tied to, for example, the cost of electricity? Those are very, very important questions. And in fact, if you talk to most data center companies as it is today, they will tell you like, sure, we can be flexible. We'll build a battery over here. You know, like don't touch the compute. We don't touch the compute. Like we want full control. We want to run it at as high utilization as we can because we want to max out what what we can do with what we have paid for. So that's a very, very good observation. I think that, you know, I mean, so is that going to always be the case? Is I think an important question. Like when we are looking at this in our research, it's of course not only a question about like what is happening like right now. We're in an incredible sort of scramble to build this new infrastructure, but you know, presumably it's going to be around for a while, and like maybe it needs to be, you know, replaced year after year, and you know, like as we heard in our other talk here today. You know, maybe if you can extend the lifetime, maybe that will decrease the capital expense that you have, and kind of edge us more towards like having to look at operational expenses. And I think it's also worth noting that like if you have numbers, you know, and maybe this will change as we have like models like DeepSeek and so on. But like when we're hearing numbers about like the amount of electricity, the cost of electricity for training some of these very large models, and that is like in the $50 to $100 million range. If you have to train and retrain these models, you know, you do that 10 times, you're at $1 billion. And so if you can slash that cost in half, it might still be a quite significant impact. And so as of right of today, I think you're totally correct in that the capital expense and sort of the rush to kind of build this infrastructure is so great. And people are still learning about them and trying to understand them. My hope is that in the future, we are going to learn about what type of workloads might be, for example, more resilient to reducing clock time without a decrease in throughput too much, for example. I mean, like, are there such things that you can play with where you maybe could, for example, be a better actor on the grid without significantly decreasing performance of the data centers? And I think my understanding of this is that this is just not a perspective that has been very prevalent in sort of the computing side before, like how you can maybe do some of the things that are helpful to the grid without, you know, compromising your own performance. And so that's one of the things that we are very interested in and kind of working on exploring with collaborators. Just to kind of try and bridge that gap between the grid, what the grid needs, what could help the grid operate more efficiently, and then, you know, what could a data center maybe contribute.
Thank you.
Thanks, Lena. Thanks, Charles, for the question. Charles, did you have a follow-up question on that one? No? Okay, great. I'm going to go back to the questions that were submitted in the chat, and we've got a question that I'm going to direct to the PhD students. For the good enough computing concept, can we also schedule error-tolerant and non-error-tolerant computing tasks based on current state of hardware available? For example, run only error-tolerant tasks when only older hardware is available.
Yeah, that's a great idea. And I think a lot of sustainable computing research has gone into the area of OS scheduling based on, like what you said, the current state. So yeah, that's something that maybe we can consider in our research.
Great. All right. Let me see if I've missed any questions here. We have a suggestion, might be great for ECE to put together a short course on data center power and cooling engineering designs. We'll look into that, Jen. Thanks for the suggestion. All right, I'm going to jump to, I think I've caught all the questions. I apologize if I've missed one here. There is one that I skipped over. I apologize. There's a question about, or a comment about an interest in technology advancements such as wide bandgap semiconductor devices and high bandwidth memories and their impact on data center energy usage. So we have quite an extensive expertise in ECE at Wisconsin on wide bandgap semiconductor devices, materials and devices, and their use in power electronics. Does anyone from our panel have a comment about advances related to either of these high bandwidth memories and their impact on data center energy usage? Is that a no? No comment?
Not from me specifically. I don't know
Yeah,
if
yeah,
Sorry,
fair
can you
enough.
repeat the question?
Yeah. So it's not really a question, it's a statement of interest
there is nothing to repeat.
in technology advancements such as wide bandgap semiconductor devices and high bandwidth memories and their impact on data center energy usage.
Okay, I can speak to the wider bandwidth part.
Oh, great.
So there's a new CXL. It's called CXL. It's an interconnect technology, and so like our plan was to leverage that because it allows for the pooling of DRAM, and then we can use like older DRAM, or we can pool old and new DRAM to have a diverse age distribution of memory. And so yeah, there are cool new technologies coming out that hopefully we can leverage to insert like our sustainability perspective into. So yeah, CXL, that's the keyword there.
Thanks, Elise. All right, so we just have a few minutes left here before we hit the top of the hour. I want to take this opportunity to express my deep gratitude to Professor Roald and Elise and Jaewon and Asmita for participating and sharing their expertise in this really important topic. I hope that we'll continue with this format with thematic presentations on timely topics as we go forward with these town halls. I want to thank all of our alumni for joining in. This has been a wonderful opportunity to connect. And for our alumni, whom I have not had the pleasure of meeting with, again, I'm Susan Hagness. I've been serving as a department chair now for the last 6.5 years. I've been on the faculty here at UW-Madison for 26 years, but in my role as department chair, one of the greatest joys I have is connecting with our alumni and hearing about your current career state and your reflections on the impact that UW-Madison has had on your professional career. So I really welcome the opportunity for those of you I haven't had a chance to meet, and those of you who I have and you'd like to catch up. Please don't hesitate to reach out. We've got a wonderful team of development directors that help facilitate meetings with me. And so think of it this way, the back porch light is always on for all of you to visit or to connect, to reconnect. Really delighted to sustain these alumni engagements. So with that, let me wish you all a very happy Thursday. Again, thanks so much for taking the time out of your day to join us. Huge kudos to our presenters, and on Wisconsin, everyone. Enjoy your day.